All right, everyone. I am here with Andrea Banino. Andrea is a research scientist at DeepMind. Andrea, welcome to the TWiML AI podcast.
Thanks, Sam. Thanks for having me.
So, you are working on artificial general intelligence at DeepMind. Tell us a little bit about where your interest in AGI comes from.
My interest in AGI comes from my background. I'm actually a neuroscientist who decided to study how the brain works, and in particular memory, how we create our memory, why we create our memory. And in particular, I'm interested in a subset of the memory field, which is called episodic memory. So episodic memory are those memory that relates to some episode that you experience in the past, in a specific location, sometimes, or with specific people. So they are also referred as autobiographical memories.
And episodic is in contrast to what other kinds of memory?
Another example could be semantic memory. So semantic is like you know the meaning of something. For example, you know what is a bicycle. That could be a semantic memory. But if I ask you to remind you to remember a specific event when you cycle with someone, then maybe now you're thinking about a specific episode in your life. That would be an episodic memory. So you relate something to a specific moment in time. It's also described as the what, when, and where of a specific event, like episodic memory.
To some degree, the relationship between memory and intelligence is kind of an obvious one in the sense that, you know, we use our memory and our prior experiences and interacting with the world, making decisions and all that. But is there a kind of broader significance to memory in the development of AGI?
Yeah, I think, as you say, it's kind of an obvious one, right? So we live in a world that is consistent. So if we gain some experience in the world, then we want to reuse that experience. We don't want to relearn every time from scratch. So you can already see how that's valuable. But something
Hmm.
that I actually study over my PhD is that episodic memory, it's also a way so it's something that enables generalization. In particular, we study how let's say if you experience two events A and B that are related together, and later in time you experience other two events like B and C that are again related together. Your
Hmm.
brain, without you doing any effort, directly relate A to C together, such that
Hmm.
you relate you do this kind of inference through your episodic memory. So if you want to give, like, if I can tell you like a more mm, precise example would be like if you see someone going out with a dog in the morning, and then you see the same dog with a different person in the afternoon, immediately your brain is going to try to connect the two people that were going out with the dog. And that's the kind of inference that episodic memory we know support. So
Hmm.
that's quite important, right?
Right, right. And what is the history of memory, in this effort to kind of get us closer to AGI? How have we used memory in the field to facilitate intelligence?
Okay, so this is, I think, a nice question, because I think in some sense the kind of memory I'm talking about is still an open question. How we do it properly in AI. We have different forms of memory currently, which we know how to play with. In particular, recurrent networks, both RNN and LSTM, are so-called working memory. So it's that gives you like imagine a whiteboard where you can write something and reason about that and then erase, because it won't stay there forever. It's like kind of a canvas where you can make predictions. That's what we know. Then we have also something called memory augmented neural networks. In that case, we basically give neural networks an external memory where they can write previous computation that they performed and then read back from there and reuse previous computation. And this gets a little bit closer to the kind of memory I hinted before, but we are not there yet. And then we have retrieval augmented models, which are those models that basically go back in a, if you like, in a table where we store almost everything we have seen in the past, like a dictionary, if you like. And then they try to look up things. But most of the time, they look up and they use that lookup to answer, but they don't consolidate back the knowledge into the weights, if you like, of the system. So they need to do the lookup all the time, which in some sense is a waste. We don't do, as I said before, we don't do that. We kind of make sense of what we retrieve and use it later.
Right. So in that latter case, you can think of it as kind of this fixed boundary between the memory and the computation in a sense, and the computation isn't ever updated. The way we think about, or the way the model thinks about its inputs, is never updated with regard to the things that it learns in the memory. It's just checking the memory constantly with each input.
Yeah, sometimes there are models for that comes now to my mind, a model where that computation is updated, but
Okay.
it's very difficult to scale up those models because they require a lot of computation. So we don't know yet how to make that model big to a scale where they're actually useful to target very complex problem. And also, we have finally the last one will be a very recent advancement in AI, which is something that everyone knows, I'm sure, transformer.
Mm-hmm.
These models have shown some of the properties of this kind of memory in language. They are what sometimes they show few shot learning, which is a prerogative of like the memory models I'm talking about. But that happens in language only, not in other domains. So I'm not sure if it's that raised the question. It's because of the model capable of doing that, or it's because of the specific domain where you train the model that allows that. So no one has done that experiment yet, but I think it could be interesting.
And can you drill down on that? How should we think about transformers from a memory perspective and exhibiting these properties that you mentioned?
First of all, I think most of the transformer that we use now in language are transformer Excel, and it's a specific instantiation of transformer whereby you add a memory and a sort of external memory at each layer of the transformer. So we already know that that's necessary in some sense to overcome some of the limits, like not having recurrence, for instance. So I would say they are limited in terms of memory also because given that we do this all-to-all comparison over the sequence, we cannot process very long context. There are now papers trying to deal with that and reduce the complexity to linear size, but still, I don't think we are at the point where let's say we can process several books and ask inference questions about books without like doing like this sort of external retrieval all the time.
Oftentimes there are ideas that we might want to apply in the context of neural networks, and a big challenge is, are they differentiable? So that we can apply techniques like gradient descent. Uh, is memory, typically differentiable? Is it typically undifferentiable? And like, how does
you
that play
touch
into?
you touch the perfect downside of like these kind of external memory where we do what is called k-nearest neighbor
Hmm.
retrieval, and that's a non-differentiable operation.
Hmm.
So that obviously has some limitations on then what you can get. And again, I don't think with the current system we know how to to do backpropagation of a very large memory. Which again, it's an open problem. I think it's a very nice problem to tackle. and we should probably start now. I think we might be able to do it.
Why does this? How does the size of the memory play into whether we can backprop over it or not?
Because most of the time you use a softmax operation over the dimension of the memory, and it becomes quickly impractical to send gradients over a very large memory, and that's because it's computationally infeasible, so it doesn't fit in memory, and also when you get with very large soft maxes, also you have problem with gradients.
There's another aspect of memory that comes to mind. We've talked about specific kind of features and uh, architectures that are used to emulate memory. But oftentimes, one of the critiques of deep learning is that the networks themselves like remember stuff, and that becomes a problem, causes problems with generalization. Are there ways that can be harnessed more directly to achieve some of your goals for episodic memory?
Yeah. Okay. I think yes, memorization it's definitely an issue. Like overfitting, it's an issue.
Hmm.
Although uh, most of what we do as well is like kind of memorize. So we enlarge our data set of experience as we grow, right? So
Hmm.
in some sense, we tend to overfit as well in most of what we do. So I don't think that's a huge problem. That's also there was actually a nice paper last year called "Direct Fit to Nature," which I recommend your listener to look up, from Uri Aston, which basically poses the same question you are posing to me, and it basically answer in this way. So we as we grow, as we have grown as a species through evolution, and also during
Hmm.
our life, we kept enlarging the kind of the amount of experience that we use to grow our brain, our network. So in some sense, we kept memorizing. It's just that we don't always start from scratch. And also, we have this ability of generalizes that I think it's still a little bit missing from deep learning. Although we should recognize this generalization is not that we can generalize to everything, right? So we have, in some sense, limited as well in generalization. Maybe neural networks are slightly more limited than us, but we already see some example of generalization which are starting to emerge in neural networks, and I think that's a good thing and something we cannot neglect. So, for instance, I had a paper couple of in 2018, so 3 years ago, in Nature, where we actually use we imbue the neural network with a representation like the one we have in the brain, in the hippocampus. And in that way, the agent was able to traverse. That was a navigation task. The agent was able to take shortcut and traverse part of the environment that were previously blocked, and the agent was able to do that with the right representation. So I don't think the problem is the backpropagation of the models themselves. It might be a problem how we train that, in terms of both the data we used and the representation that we forced to emerge.
You mentioned this paper that implemented something akin to the representation that's used in the hippocampus. What is that representation? How does that work, and how?
The paper we had we studied this thing called grid cell. So in the hippocampus, grid cells, yes. So in the hippocampus, we have so it's a memory machine of the brain, but it's also the spatial machine, right? You can see also spatial as memory, but that's not going into that. There's a whole field that I don't want to go into. But basically, we have the two cells that are probably the three cells that are more known, like head direction cell. So those are cells that fires every time you look in a certain direction. But I'm talking about allocentric direction. So every time you face north, there will be a cell firing with a certain probability distribution over north. and the same for the other allocentric direction. And the north is not the cardinal north. The north is the, let's say, is the one with which relate to a certain reference point in the environment. So let's say, okay. Then we have place cell. Those are neurons that fires every time you are in a particular location, independently of where you're looking at. And then we have grid cells, which are these visually and mathematically beautiful cells that basically fires following an hexagonal lattice. They have a 60-degree offset, and they are very beautiful. And there have been several theories that try to motivate the reason why we have that. And one of these was because we can use that to calculate shortcut, to calculate the shortest vector between 2 points. And we manage to do two things in that paper. First of all, we managed to make the representation emerge in a neural network, trained to do path integration, so to do a navigation task. And secondly, we use those representation in a reinforcement learning agent, and we prove through several ablation as well that that was the only agent able to take shortcut. And if we lesion, let's say, some grid cell, the ability of the agent to take shortcut just went down. So it was kind of an empirical paper to prove what the grid cell are for.
Is the idea in terms of the implementation that I'm imagining you're like adding sine and cosine elements to your loss function or something like that,
No,
or
no,
is
no,
it
no, no,
more kind
no,
of
no, no.
data driven?
It's data driven. That our goal was
Okay.
really to be super data driven, and
Okay.
we achieved that by actually a specific was a recurrent architecture. Two things were really important. One was to introduce a dropout such that not all neurons were able to fire at the same time. And the second one
Okay.
was introduce noise in the gradients. And that basically helped.
But those are the two things we always want to do, right?
Yeah,
They
but
don't
it's
seem
also
particularly specific to this problem.
that's probably why people like so much that kind of paper, because it was kind of a
Right.
general approach to make that. One of the, although I have to say it was kind of difficult to analyze, but one of the reasons why noise helps, because it helps you moving away from a certain solution in the landscape of the loss. And
Mm-hmm.
our way to work was to help the network going down the solution we liked, so grid cell. But that wasn't too difficult actually to achieve,
Okay.
and that's why I think it was a nice piece of work. Yeah.
Interesting. So I'm trying to speaking of memory, I'm trying to remember how we got here. We're
Actually,
talking a little bit.
the Ponder stuff. I guess you invited me to talk about the PonderNet,
Yeah.
and it's inspired by memory, exactly from the study that I mentioned at the beginning. This thing about doing inference,
Uh-huh.
associative inference, that was part of my PhD, and one of the papers that came out during that time was this ability of the hippocampus to basically do this recursive pondering before actually being able to do this sort of inference. So you see people, when you ask people, when you ask, I remember doing this experiment practically with people, and when you ask them to relate A and C, to tell you a story about AC, they think more. They really spend more time in thinking compared to A, B, and B, C. And that's how I got inspired, because our brain works, so the same mechanism, because when we did then fMRI study, right, the same mechanism was involved. It's just that the answer was going out of the hippocampus and then back into the hippocampus few times, but then was processed by the same system, if you like. And I think that's a nice property to have in an algorithm.
Does that mean I'm probably taking this too far, but when I hear you say that, I make associations like the brain knows how to do scanning and it doesn't have something like an inner join.
Okay. No. the I mean, the problem there is that what does it mean, the brain? No, I guess from a computational perspective, then I could ask you, what's the loss that the brain is minimizing then to do that? Which I don't know. I don't know the answer. Maybe I don't know. Maybe it could be uncertainty reduction, because at the end of the day, we want to get better prediction. We want to be able to, I think, better predict the model, the world, because it's then it would be less uncertain and so less risky. But I think there are people like much better than me that could explain that.
Yeah, yeah. No, I think that was going in maybe a slightly different direction. I was inferring from what I heard you say was that when we ask people to do these kind of associative types of tasks or inferences, where they need to get from A to B and B to C, that takes longer, which kind of suggests that there's not some built-in associative thing in the brain.
No, because in the fMRI study that we did, we saw that also if we do longer inference, we are still
Mm-hmm.
able to do that. It just takes more time, even more time.
Mm-hmm.
So I think that the algorithm we apply is the same, which is the ability of making associations. It's
Mm-hmm.
just that the longer the jump that I ask you to do in
Mm-hmm.
doing this sort of associative mechanism, the more you need to do. You do it a bit hierarchically, right? You put, I don't know,
Right.
the things that are just 2 steps separated, you calculate that, then 3 step, and then you might be able to put together 2 and 3 and do 5.
Mm-hmm. So we went down this particular rat hole in trying to provide some context for PonderNet, which I'll have you explain, but I still don't really see the connection with memory. When I read the abstract for PonderNet, I think about things like hyperparameter tuning and like early stopping, like the way we train networks and like pulling that into the network as opposed to anything having to do with memory and the stuff we were just talking about.
Yeah, yeah,
So
okay.
tell me more about the connection.
Two-way answer about the connection. The first
Okay.
one is the more high level, uh, maybe and wavy if you like. It's generalization. So we believe that mechanism like PonderNet
Mm-hmm.
can get you a little bit far in terms of generalization compared to not doing pondering in deep neural networks, and that's the kind of things that we discussed before, right? So one of the benefit of memory is you're giving you the ability to have the right input to generalize, I guess. Let me put it this way. The second is that a previous work to PonderNet was another work I did during my PhD, which was called MEMO, and was a memory augmented neural network, where we studied this mechanism of recirculation. So the network spit out an answer, you compare it with previous answer, and you only give the final answer to a certain problem when you are satisfied. So you were already already implementing this sort of pondering mechanism. But there it was really, really early stage, because we use basically reinforcement learning to train a Bernoulli variable that was basically saying go or stop. And we saw that this was really hard to train and very noisy in terms of variance. So we
Mm-hmm.
decided to do something more principled, and that's what led us to PonderNet.
Okay. So taking a step back, what's the problem that you're trying to solve with PonderNet?
Yeah, I think that's the first line of the abstract, which basically says that normally neural networks, so the amount of computation that we spend in neural network grows with the size of the input, but not with the complexity of the problem.
Mm-hmm.
But as we just mentioned, like few minutes ago, that's not how we reason, right? The more complex the problem, the more we spend time on it,
Mm-hmm.
and that's what we wanted to get essentially with this work. And also we
Got it.
wanted to make it fairly general, such that it could be applied to any architecture. That was, yeah, to be architecture agnostic.
Got it. And so the size of the input we know what that means. We're talking about like feature dimensionality.
Yeah.
We know the problems that come along with that. Complexity of the problem. What exactly does that mean, and how do we measure that?
Okay. I think empirically, again, we have like the example I like in the paper is that it takes more to divide than to sum. So that's exactly the same problem, mathematically speaking, but for some reason we spend more time dividing than doing summation.
I mean, it's fair to say that we're talking about the computational complexity of a given problem as opposed to some conceptual type of
Yeah,
complexity,
yeah. So
right?
if you have to
And
apply the same algorithm
yeah,
to, the algorithm is the same. It's just that the specific instantiation where you have to apply it requires more compute time. So it's like a computer, right? So it's the same. You apply the same function, but in some circumstances it takes more time. So the computer thinks more. That's not how neural networks work now. It's they imply the same amount of thinking for each input. I can give you another example. In a sentence, for instance, when we read, we don't spend the same amount of time gazing each single word in a sentence. So that's been proved in psychology. So we tend to focus our attention on few words in the sentence that are more important to process the whole thing. So that's another practical example.
okay, okay. Um, and so you want to create a neural network that, um, would you describe it as kind of budgets its, computational investment in solving a problem according to the inherent complexity of the problem? Is that a way to think of it?
Yeah, I would say it's a fair description.
And so, how did you do that in PonderNet?
Okay, so important. First of all, this is based on a previous work called adaptive computation time,
Hmm.
and the problem there is that there they directly minimize the number of pondering step, so the number of step the network took. Whereas in our case, what we did was to make this probabilistic. So to be slightly more practical on this, for each time step in the sequence, we calculate the prediction, the probability of halting, and the next step. So the probability of halting is just a Bernoulli random variable, which tells you the probability of halting at this particular step, given that you have not halted in previous step. And then from there, what we can do then is to calculate a probability distribution by basically multiplying the probability at each time step in order to form a proper distribution, a proper geometric distribution. Once we have that, what we can do is to basically weight each single. So we calculate the loss for each prediction in the sequence that we made, and then the loss is then weighted by the probability of having altered at that particular step. And that's a critical difference between us and ACT, because in ACT, they instead output a weighted average of the prediction. So they don't output a specific prediction, but a weighted average of the whole prediction. And that creates a bias in the gradient. Whereas in our case, we can basically just really take the exact loss at each time step, given the decision of halting. And then we take the particular training time, we take just a particular step that has a threshold that basically surpassed the threshold that we decide for halting. Whereas at test time, we just sample from the probability distribution that we learned.
Okay. I mentioned earlier that it calls to mind, you're talking about halting here, calls to mind early stopping. Is the idea that, early stopping is kind of like, we're trying to conserve training time? Is the idea here that we're trying to conserve inference time? Like we
Yeah,
have an
exactly.
input, we're trying to make a
Yeah,
prediction.
yeah,
Instead of going through the whole thing, let's keep going until we're sure what the answer is and then stop early. And
Yeah.
this is an approach to getting there.
Yeah, I think our hypothesis was that you can, let's say you want to implement an algorithm on your phone, you can train it in the cloud, no problem at training time, right? The amount of compute, forget for few people, no problem. But then at inference time, you want to be quick, and
Yeah.
that's important. But now I'm laughing a little bit, but if done properly, I think this could help also reducing the amount of resources that you spend at training time. Because we actually have an experiment in the paper where we see that the total number of gradient updates for PonderNet are smaller than other methods, given the same final performance. So this could also help reducing the amount of resources that for certain people, I guess.
Okay. And then circling back, the connection to memory here, is it in storing these probabilities and the Bernoulli variables, that kind of stuff, or is there a different connection?
Yeah, I guess we left the connection with memory maybe a little bit behind because,
Okay.
however, you might think. I remember one tweet that actually also inspired this work a little bit from Andrea Carpati. That was basically say one of the limitation of transformer is actually they spend the same amount of compute for each token in the sequence. So if we treat, broadly speaking, again a little bit like transformer as a form of preliminary memory, right? You can think of applying this on top of transformer and see if that could help, right? Maybe spending different amount of compute per point in the sequence.
Got it. So,
I understand it's a bit stretchy, but
yeah.
it's an avenue.
It's kind of it's an analogy of some sort. It's not necessarily an implementation of a memory system that we're talking about here. Is PonderNet is a specific network architecture as opposed to a technique that you could apply to different architectures, or is it the latter?
It's a technique. So it's
Okay.
really, it's indeed, if you see in the paper, the step function, what we call S in the paper, could be anything. Could be an RNN, a CNN, a transformer,
Okay.
an RL agent, whatever. As long as you return, so as long as you add this extra unit that calculates the probability of halting, you can apply it to everything. That was important for us. And indeed, in the paper, we do that. So we applied it 3 different architectures.
Okay. And how did you evaluate the results?
So we use one task from the ACT paper called the parity task. So you have a string of 1 and 0 or 1 and -1, whatever. And you need to calculate the parity of that string. So it could be either odd or even, right? And the good thing that we could, that's a nice task because you can also train on parity up, let's say in our case, up to 48 integers, but then test up to twice as long the length to test this ability to extrapolate. And indeed, we see that our network extrapolate much better than baselines, the other methods. Then we applied it to a reasoning task, which is called Babi. And basically, you have 20 tasks which you train all in parallel. It's a language task where you get asked questions.
Actually, can I pause you and go back to parity?
Yeah.
I'm trying to work this through in my head. Like, okay, so I guess the first thought that occurred to me is with some number of bits that you're trying to calculate the parity for, it's not like you're trying to add the bits together and as soon as you hit a 0 or something like that, you know the answer, right? You need to look at all of the bits
Yes.
and the input for parity,
Yeah.
but the premise is that independent of that particular fact, inside the network, you could still stop early relative to going through some number of computations
And still answering the right
and still
question.
answer the question correctly.
We have a baseline. We pick this task exactly because we know this is a task that, like a normal RNN, is having trouble
Okay.
doing. Yeah,
Got it.
that's a kind of a well-known issue in this sort of literature.
Okay. Got it. Yeah, on the topic of transformers, which have come up a couple times, you did a workshop at ICML talking about transformers and reinforcement learning. Can you talk about taking two topics that people are really excited about and combining them together? Tell us a little bit about the goals of that work.
So I think I really got inspired by the BERT work, where they have this non-causal masking. And in RL we keep using LSTM essentially for doing most of the task, but we know that they suffer from what is called regency bias. So they tend to pay attention only to the last bit of the sequence that they are trained on, which, to be honest, for most of the environment that we use nowadays, it's fine. But if you grow in size and the context you want to pay attention to is quite long, then they start to suffer. So one option would be to use transformer, because we know that they can handle longer context than LSTM. However, the problem in RL is that the reward are sparser most of the time, and the gradient had been shown to be noisier. So it's difficult to train so many weights. So what we did in that work was basically to generalize the BERT training to, which is done on tokens. So those are like categorical numbers, so that you can apply softmax on the other side. We generalize the BERT masking to real value numbers input, so to basically features. So we send the features from the CNN into the transformer. We mask some of them, and then on the opposite side, we basically use a contrastive approach to reconstruct the masked input. So we give some negative taken from the same sequence, and positive, and the network has to discriminate. And also, what we did in that work was to combine LSTM and transformer in the same architecture. And the good thing about that is that it helps you reducing the size of the transformer to gain in speed. So because and we let the agent actually learn when to use when to use LSTM alone, or when to combine transformer and LSTM, such that in some tasks it can basically avoid the extra complexity of the transformer and just use the LSTM, whereas in other more complex tasks it will focus on using both.
Got it. And so, in a sense, there are echoes of the PonderNet paper in that you're trying to manage the computation or let the agent manage the computational investment based on an assessment of complexity.
In some sense, yes, through the RL gradients there. So that
Hmm.
was really the agent, by playing with the environment, that was deciding what to use. Because yeah,
Hmm.
it's, although I would love to actually have agents that stop and ponder. That I think would be nice.
Uh-huh. What types of problems did you experiment with
We
for this paper?
three different domains: the whole of Atari suite,
Okay.
DeepMind control suite, which I'm particularly proud, because that's something that normally with of policy methods like the one that we had there, we didn't do so much work. And then DeepMind laboratory, which is a suite of 30 tasks, 3D complex tasks that you play all at the same time. So it's also flavor of multitasking at scale. That was the task, really at scale.
Hmm. And from a performance perspective, what kind of results did you see? Was this, promising enough to keep poking around at, or was it, really good performance that, kind of challenges state of the art?
Look, first of all, we always improve on data efficiency massively compared to baseline. And
Mm-hmm.
in many domains, especially in DM lab, so the DeepMind laboratory, we actually also got state of the art performance,
Okay.
which was so. And that's good, because that was the more complex domain where we played. So
Hmm.
I think, and I think that was kind of not an issue, but something we could have done slightly better to focus more and more on complex domain, because I think that's where this kind of method will shine. So like complex architecture probably will benefit more from like complex method. Although I still think it's something I'm quite passionate about. I think there's lots of stuff we can do to improve transformer and memory in general in reinforcement learning, especially in relation to the length of the context that we can process. That's something I think important and kind of a bottleneck, in my opinion.
Meaning the approach you took in this work of coupling the LSTM and the transformer and allowing the agent to choose, sounds like you're saying that's kind of a beginning place, but there's a lot more to be done there.
I think so. As for us, we have different sort of memory. As I said before, we have very long-term memory. We have short-term memory. I think I'm not the first one to say this. There are a few papers out there yet already, and where they argue, and I argue, that agents should be equipped with this sort of different time scale memory.
Awesome. Well, Andrea, thanks so much for taking the time to share a bit about what you're working on.
It's been a pleasure, Sam. And again, thanks a lot for inviting me. It's actually an honor.
Absolutely. Thank you so much.